Good morning, students. Welcome to video lecture on microwave and optical fiber communication. Subject code U18EC709. Topic ferrites. Ferrite devices. Ferrites are non-metallic material with resistivity nearly 10 power 14 times greater than metals. Mu permeability of the order of 1000. Relative permittivity, dielectric constant around 10 to 15. Ferrites are oxide-based compounds having general composition is of the form MEO Fe2O3, that is MEO Fe2O3. They are obtained by firing powdered oxides of materials like MNO, ZNO, CDO, and NiO at 1100 degrees centigrade or more and pressing them into different shapes. Ferrites have atoms with large number of spinning electrons, resulting in strong magnetic properties. Polarization of the electromagnetic wave. Here you can observe linear polarization. In linear polarization, the electric field is having either X component or Y component. In circular polarization, the electric field is having both the electric field components along X and Y direction, and they are equal. In elliptical polarization, the field is having both the components along X and Y, and they are not equal. You can observe. Polarization is nothing but it is the direction of electric field at a given point as a function of time. Now, polarization of an EM wave. You just consider a linear polarization. In linear polarization, the electric field is having either X component or Y component. If X component, this can be written as Ex naught e power minus alpha z cos omega t minus beta z some Ax cap Ay. Ey is equal to Ey naught e power minus alpha z cos omega t minus beta z Ay cap. The electric field may be having either X component or Y component. Now here consider a linearly polarized wave traveling X polarized traveling along Z direction. You can consider. Now let it be Y axis, it is X axis, and it is Z axis. Now here the electric field is X polarized means uh, the electric field is along X direction, and here the wave is traveling along Z direction. Okay. Cos omega t minus beta z. Minus beta z includes the electromagnetic wave traveling in positive Z direction, and the polarization of the electric field is along X direction. If it is traveling along if it is Y polarized, then this can be represented as the wave Y polarized traveling along the direction. In this fashion, you can represent. If the electric field is having both the components X and Y, the resultant electric field traces circle. If they are equal, the resultant electric field traces ellipse if Ex and Ey are not equal. Non-reciprocal property of ferrite materials. Now here consider a ferrite material, two circularly polarized, one rotating clockwise and the other anti-clockwise. Now here you just assume some first signal is rotating clockwise direction, and the second signal rotating in anti-clockwise direction are made to propagate through the ferrite rod. Now here, for proper operation, a strong magnetic field is to be applied for ferrite rod. Uh, Here these two signals, one rotating along clockwise, another rotating along anti-clockwise, are made to propagate through ferrite. The material reacts differently to the two different rotating fields, thereby presenting two different constants to the polarized waves, such that mu r1 epsilon r1 rho1 for left circularly polarized waves. It presents mu r2 epsilon r2 and rho2 for right circularly polarized wave. Faraday rotation. When a linearly polarized EM wave along x-axis at t equal to 0 is made to propagate through the ferrite in the z direction, the polarization of the wave rotates with distance, and this phenomenon is known as Faraday rotation. Now here, just assume that this particular wave is x-polarized and traveling in z direction. Here it is a ferrite rod. You just assume the moment of polarization in ferrite rod. It is the direction of propagation in the ferrite rod. Here some ferrite rod is placed. It is ferrite rod. Now it is the initial polarization of electromagnetic wave at t is equal to 0. When this particular EM wave made to propagate through the ferrite rod, after traveling some distance, the polarization of the wave gets rotated either in clockwise direction or in anti-clockwise direction based on the material. Here we are assuming the polarization of the wave gets rotated in anti-clockwise direction, and here the amount of rotation depends on the length of ferrite material. After crossing the ferrite rod here, you can observe some amount of rotation in polarization of the electromagnetic wave, and the polarization of the wave rotates with distance. This phenomenon is called Faraday rotation. Faraday rotation. Just now I explained. Uh, Once again, I will draw the diagram. It is the direction of propagation. Let it be y. It is x at t equal to 0 position. How the wave gets rotated at different time instants, you can observe. The amount of rotation depends on the length of the rod. Now here, when it is a ferrite material, some EM wave linearly polarized is meant to propagate through a ferrite. For proper operation here, we have to apply some permanent magnetic field. It is port 1 and it is port 2 of ferrite rod. When it is made to propagate through the ferrite rod, you just assume uh, the rotation is in anticlockwise direction. Even if the wave is made to propagate through the ferrite rod through port 2, the rotation is in the same direction. Either the electromagnetic wave travels from port 1 to port 2 or port 2 to port 1. The rotation is in the same direction in case of ferrite rod. Now here the micro devices which makes use of Faraday rotation are gyrator, isolator and circulator. Gyrator is a two-port device. Uh, it offers, it is port 1, port 2, it offers 180 degrees phase shift from port 1 to port 2 and 0 degrees phase shift from port 2 to port 1. You can observe the S matrix of gyrator. I will explain how The rotation takes place from port 1 to port 2 and from port 2 to port 1. In the next slide. Now it is the structure of gyrator. It is having some rectangular waveguide, some a twisted circular waveguide is attached. It is circular waveguide, and at the end, once again, a rectangular waveguide is attached. It is a tapered ferrite rod. Now, let us check the operation of gyrator. Consider the diagram. It is a rectangular waveguide. To that rectangular waveguide, a twisted circular waveguide is attached. It is a rectangular waveguide. This circular waveguide, it is also circular waveguide, and it is a rectangular waveguide at the end. Now here it is port 1, it is port 2. When an EM wave traveling from port 1 to port 2, you just assume uh, this particular twist offers 90 degrees in anti-clockwise direction, and from port 2 to port 1, it offers 90 degrees rotation in clockwise direction. Means here twist offers rotation in opposite direction. When it is traveling from port 1 to port 2, it offers 90 degrees in anti-clock, and port 2 to port 1, it offers 90 degrees in clockwise direction. And consider a tapered ferrite rod which is placed inside the circular waveguide. Uh, Now here you just once again assume uh, ferrite rod offers rotation 90 degrees in anti-clockwise direction. Means when the wave is traveling from either port 1 to port 2 or port 2 to port 1, ferrite rod offers rotation in the same direction. So when the signal is traveling from port 1 to port 2, what is happening? You can observe. Uh, uh, just consider this is the initial polarization of electromagnetic wave. After crossing the ferrite rod, the polarization gets rotated by 90 degrees. Sorry, after crossing the twist, the polarization of the electromagnetic wave rotated by 90 degrees, and after crossing the ferrite rod, the polarization once again rotated by another 90 degrees, and at the output you will get the 180 degrees phase shifted signal. Now, in this fashion, you will get the 180 degrees phase shift from port 1 to port 2. Now, you can verify from port 2 to port 1, this particular device offers 0 degrees phase shift. Now it is the initial polarization at port 2, and there is no rotation, there is no change in direction of rotation for ferrite rod. Ferrite rod offers a rotation in anti-clockwise direction. So this particular device, after crossing the ferrite rod, it is 90 degrees rotated in anti-clockwise direction, and after crossing the twist rotation is in opposite direction, so it re-rotates the signal to its original position. uh, at the output of port 1 you will get 0 degrees phase shifted signal. In this fashion, the device gyrator offers 180 degrees phase shift from port 1 to port 2, and 0 degrees phase shift from port 2 to port 1. I think you are clear about the operation of gyrator. The next is isolator provides a small amount of attenuation from port 1 to port 2, maximum attenuation from port 2 to port 1. That is, here it is a 2-port device. It offers a very small amount of attenuation from port 1 to port 2 and maximum attenuation from port 2 to port 1. And for that reason, it is always connected nearer to the microwave source to cut the reflections from the load towards source. Microwave bench, you can observe the position of isolator always it is connected nearer to the source. It forwards the signal with minimum attenuation, cuts the reflection from the load towards source to avoid damaging to the source. Uh, Here it offers minimum attenuation from port 1 to port 2. That is why uh, the symbol is mentioned here. From port 1 to port 2, it offers minimum attenuation, and that can be indicated by the arrow. Uh, Let us move to the operation of isolator. A small change in structure. Everything is same except a small change. Uh, it is a rectangular waveguide. It is a twisted circular waveguide is attached. It is circular waveguide, and at the end, a piece of rectangular waveguide is attached. You just assume from port, it is the position of port 1 and it is the position of port 2. From port 1 to port 2, uh, the twist offers 45 degrees anti-clockwise direction. From port 2 to port 1, the twist offers 45 degrees in clockwise direction. Now here a tapered ferrite rod is placed which offers a rotation in clockwise direction, a 45 degrees clockwise direction, and some resistive card is placed inside the rectangular waveguides. At the input side and at the output side, two resistive cards are placed in such a way that uh, these two resistive cards are in the same plane. The two resistive cards are on the same plane. And one more important thing is you just assume uh, this particular plane of resistive card, polarization of electromagnetic wave, they are perpendicular. Then only the signal will come out of the resistive card. If the plane of resistive card is parallel to the polarization of electromagnetic wave, uh, the electromagnetic wave will not come out of the resistive card. Now here I am assuming this particular vertical signal is this particular polarization is perpendicular to the plane of resistive card. So the signal will come out of the resistive card. Now it is the polarization of initial polarization of electromagnetic wave. It is perpendicular to the plane of the two resistive cards. Uh, this particular polarization is perpendicular to the polar plane of resistive cards. So you will get the electromagnetic wave at the output of resistive card. The signal will pass through the resistive card. And after crossing the twist, the circular waveguide twist offers 45 degrees rotation in anti-clockwise direction, and after passing through the ferrite rod offers rotation in clockwise direction. Uh, rotated back to its original position, and this particular polarization is perpendicular to the plane of resistive card. So the electromagnetic wave will come out of the rectangular waveguide with minimum attenuation, and that is the way of how an isolator offers minimum attenuation from port 1 to port 2. Now you can observe when some signal is applied at port 2, in what way it is offering infinite attenuation, you can observe now. Now it is the initial polarization of electromagnetic wave. This particular initial polarization is perpendicular to the plane of resistive card, and after passing through the resistive card, uh, the ferrite rod rotates the polarization of the electromagnetic wave by 45 degrees in clockwise direction, and when the wave is traveling from port 2 to port 1, twist offers another 45 degrees rotation in clockwise direction. So the electromagnetic wave polarization rotated by 90 degrees. Now here this particular signal, this particular polarization is parallel to the plane of resistive card, so it will not come out of the resistive card. Resistive card completely blocks the signal, and that is why you will get, in ideal case, you will get some zero signal. You will not get any signal at port 1. In this fashion, the device offers a minimum attenuation from port 1 to port 2 and maximum attenuation from port 2 to port 1. You can observe uh, a resistive card twist ferrite rod, one more resistive card. These two are in the same plane. Initially, this particular polarization will be considered as perpendicular to the planes of the resistive card. Then only the electromagnetic wave will come out of the resistive card. When it is applied uh, after reaching the second resistive card, this particular polarization of electromagnetic wave is perpendicular to the plane of resistive card. You will receive the output signal with minimum attenuation, and when the signal is applied at port 2, it is rotated by 90 degrees in such a way that the polarization of electromagnetic wave is parallel to the plane of resistive card. So no signal will be received at port 1. And this is the S matrix of isolator. It offers minimum attenuation from port 1 to port 2. Port 1 is perfectly matched with the junction, port 2 is perfectly matched with the junction, offers infinite attenuation from port 2 to port 1. You can observe when the signal is traveling from port 1 to port 2, twist offers 45 degrees in anti-clock, ferrite offers 45 degrees in clockwise direction, overall phase shift is 0. So the two resistive cards are in the same plane. They will allow the electromagnetic wave to pass through them. And when the electromagnetic wave is traveling from port 2 to port 1, this rotates the polarization by 45 degrees. In clockwise direction, ferrite rod rotates uh, the polarization by another 45 degrees. The total phase shift is 90 degrees. And now, when the wave is traveling from port 2 to port 1, the polarization of electromagnetic wave is parallel to the plane of resistive card. So, the resistive card, the second resistive card, which is kept inside rectangular waveguide of port 1, it completely blocks the electromagnetic wave. Now, multiple section inside isolator for better signal blockage. Thank you. We will meet with the next lecture.